questions? So hopefully and also in terms of, so those of you who are taking the course rather than listening, I think, well, maybe we can, I don't know the format, so I don't know what's required, but I have problem sets that I can give you. I think that's probably the best. If you want to do a research project, that's even better. But we'll maybe talk that over with Andre once he arrives. Okay, so so today I'll talk a little about the first people who worked on surface tension and why they were interested in it. And then some more about why surface tension is important, why modern scientists are concerned about surface tension, and then we'll start getting into the physics of it. So where does it come from? Okay, so the first people to look at surface tension, so Hero of Alexandria was called the greatest experimentalist of antiquity, and he was, these were the good old days where people were mathematicians and engineers and philosophers and artists all in one, and he came up with a number of inventions describing, which relied on surface tension. So in particular, he looked at clocks, a water clock. So if you have a water clock, so let's just imagine we have a continuous flow of fluid somehow, and we want to make it discrete, right? So we want something which counts seconds. So how do you do that? Well, you can do that with surface tension. If you have a continuous flux Q, then of water, then basically, if we know it's coming out of a tube here, it will grow until reaching some critical volume, which we'll soon know how to do, and then it will pinch off and release a drop. Okay, so despite the fact that you have a continuous flow, you get discrete drops emerging, and this was the sort of basis for the first clocks, which were developed by Hero. Okay, and Pliny the Elder was another sort of polymath who was good at everything, and he described the glassy wakes of ships. So if you see ships, when you notice ships coming into the harbor, you'd see that there was a very, despite waves just about everywhere, there were regions where it was completely flat. And this has to do, as we'll see, with the entrainment of biomaterial. So biomaterial is just waste which is suspended in the water column. It's actually surface active, which is to say it sticks to the interface, it reduces the surface tension and makes the interface behave like an elastic. And so this is why when you're swimming in a pool or swimming in a lake, if you swish water up, you get these flat regions. And so he noticed this in the wake of ships. And I also like this quote a lot, which is really why I included Pliny the Elder. And then he mentioned truth coming out in wine. So we mentioned this last time, and so this is the first. So this was written by King Solomon, thought to be the wisest man that ever lived. So if we were to translate this into a Brazilian, it would say, stick with the wine and don't touch the pinga, okay? Because, so this is Old English, so I don't know, who hath sorrow, who hath woe, so who's sad? Those that spend too much time with the wine. Then don't look at the strong red wine that moveth itself aright, which means that it climbs in the glass. At the end, it bites like a snake and stings like a different type of snake, an even worse snake. Okay, so when it says moveth itself aright, so this is of course a translation from the Hebrew, but I had a Hebrew scholar translate this, and it always says that moveth itself aright. So it's true that when you have a strong liquor, then the fluid actually climbs in the glass. Okay, and so this is true in wines, particularly fortified wines, so port. And I was explaining this last time, but we'll go through it again in case you didn't catch it. But if you have this thin layer of wine, which you get from taking a sip or swirling your glass, then you get evaporation of alcohol. So it's basically an alcohol-water concentration. Alcohol, water, and some sugar. This is the basic ingredients of wine. And alcohol is volatile, so alcohol evaporates from everywhere, but because in this thin film region you have a large surface area to volume ratio relative to the bulk, right? So the same amount of evaporation here will decrease the alcohol concentration much more than in the bulk. So the thin film then becomes depleted. It has less alcohol than the bulk, which means that its surface tension is higher. And the surface tension is a force per unit length, so it's a tensile force, and this then pulls fluid up the sides of the glass. And so you have a flux up the walls of the glass, and this gives rise to this band. So fluid sweeps up to it, hits the top of the film, then it accumulates in this band, which then eventually falls owing to the influence of gravity. Okay? And so again, this is something in the Bible, King Solomon is in Proverbs is warning against drinking the sorts of drinks which do this, and cachaça certainly does. Okay. So this is also, surface tension was also considered by Leonardo da Vinci. I have a friend who's insistent that Leonardo da Vinci is given too much credit for all of the inventions in the world, and he says and he insisted it's because Europe did not want to give credit to the Arab world, so a lot of great scientific inventions came up through North Africa, through the Moors into Spain, and then when they were expelled from Spain, suddenly Leonardo da Vinci is credited with having invented everything, and there's even some indication that he had access to the Arab libraries. But in any case, it is sort of true that, I mean, I don't know the extent to which this is true, but it is true that a lot of he sort of has very heuristic, has a sketch of a helicopter. It's like, Da Vinci invented the helicopter and so forth. So it's not entirely clear what his contributions were and the extent to which he was simply publishing others' ideas. But in any case, he did report capillary rise. So capillary rise, we know if we have a straw, if we put it in water, then the water will climb up the straw, and the smaller the straw, the higher it will go. And so he suggested that mountain streams are being fed by a capillary network. So you imagine you have a mountain which has tiny cracks in it, and the water is then, he suggested that the water is then climbing up spontaneously through capillary action, feeding these streams. Okay? So Francis Hawksby I'm always interested, as you could probably tell from that last digression, in scientific history, and in particular scientific scandal, and Newton. There are all sorts of nasty stories about Newton, but here's another one. Francis Hawksby did these experiments on capillary rise, and they were very carefully done. But this is basically described by Newton, and who gave no credit whatsoever to Hawksby. And now we have, which is why there's no picture of Hawksby on Wikipedia. So, but here we have, so Benjamin Franklin, he was an American polymath, politician, scientist. He was, as we mentioned last time, he was interested in, he noticed when he was traveling in Bermuda that the spear fishermen, in order to flatten the surface, they would throw oil on the water to suppress the waves and so not distort, make it easier to hit their targets. And I think it's interesting here because he did this experiment, and he was basically looking to see how far a teaspoon of oil would spread on a pond. So he looked on a stationary pond, and if he'd asked the right question, he could have got something much more important, which is the size of the molecule. Because if you put down a spoonful of oil on water, it will go out to one molecule, and so from this you can calculate the size of the molecule from the area and the initial volume. Andre, welcome. So now things start getting a little more serious, and people start writing down equations. Laplace was a French mathematician and astronomer, and he looked at the meniscus. So the meniscus is the shape of an interface when it adjoins a solid, and so this is called, I call often a curvature pressure, or Laplace pressure is a pressure that arises as you cross an interface, and it's proportional to both the surface tension and the local curvature of the interface. And this is called, again, the Laplace pressure. So Thomas Young was another so-called polymath, which means he's basically good at everything. He did solid mechanics, so Young's law. He was a scientist. He also translated the Rosetta Stone. So he was an incredibly talented character, and he also looked at the nature of light with ripple tank experiments, and he looked at the description of, he looked at the wetting of a solid with the fluid. So when you put a blob of fluid onto a solid, what shape does it take? There's something called Young's law, which we'll come to next class. Okay? So Plateau was actually a Belgian scientist, but he was working in Paris. He lost his sight, but continued to work through his son-in-law in the laboratory. So he did a lot of work on soap films, minimal surfaces, drops and bubbles. He was interested in modeling the shapes of planetary bodies, so astrophysical bodies, planets. We know they're basically, gravity wants to keep them spherical, but rotation distorts them into oblate spheroids. And so it's, of course, very hard to model gravity in the lab, but you can use surface tension, because surface tension also wants to maintain the sphericity of a body, so you can then have a balance between surface tension, which keeps things spherical, and rotation, which again flattens them out. And so it turns out that the progression of shapes you get when you have this balance between surface tension and rotation is the same as the shapes you get when you have gravity and rotation. So he actually modeled then the instabilities you get in astrophysical bodies, so in heavenly bodies. So it's kind of interesting because you have, and we'll actually go through this, but if you have a rotating sphere bound by surface tension or bound by gravity, as the rotation rate increases, it goes from spherical to oblate, so it's basically axisymmetric, but then at a critical value it goes into hot dog shape, right? So it actually breaks axisymmetry, and then these things will go unstable. That's true when the restoring force is either gravity or surface tension. Okay, so now we get into who cares about surface tension, apart from me, and hopefully you. So the first things to care about surface tension were bugs. So as we'll see later in the class, surface tension dominates gravity on a scale which is small relative to raindrops. That is to say, when things are on the order of millimeters, and most creatures, certainly all insects, have functions which operate on that scale. Okay? So if you actually look at the distribution of the size of all living creatures, there's a huge peak in the insect range. So there's an incredible amount of diversity in the insect world, and these guys live in a world dominated by surface tension. So for the last 10 years, I've looked at a lot of mechanisms arising in biology dominated by surface tension. Okay? So they use surface tension for weight support and propulsion at the water surface. They have to be able to deal with raindrops. They have to survive raindrop impact. We saw last time that they can adhere and de-adhere to surfaces, so they can climb walls, they can climb ceilings using surface tension. And these are some rather, this is one of the strangest things I've ever seen, actually. Okay, ready? So these guys use bubbles for hunting.
Far from being quiet, the ocean is filled with a cacophony of animal noise that can even disrupt the sonic transmissions of submarines. Most of the din is made by a surprisingly insignificant creature, the pistol shrimp. By snapping its claws, it can not only make communication sounds, but something far deadlier. These shrimps are its prey.
These shrimp are its prey, they say.
It deals a knockout blow from a distance by using its claw as a sonic weapon. First, its claw is cocked like a pistol. Then fired. The effect is literally stunning.
The sound effect.
As the claw is shut, it fires a blast of bubbles. Incredibly, as the bubbles collapse, they momentarily reach the temperature of the sun. This implosion causes a shock wave that stuns.
Right, and so they basically release a jet of water, and the speed is so high that you go below the cavitation pressure. So that's the pressure at which bubbles come out of solution. And so then these bubbles collapse, and the resulting shock wave stuns their prey. So they basically direct the bubbles towards the prey and stun them. Okay,
So the shrimp feels like a pressure wave that knocks them off?
yeah, that's right. That's right. So the closer you get to the bubble, the better, right? But and they said that it gets the temperature of the sun. There's something called sonoluminescence. I don't know if you've heard of it, but there's something just discovered about 10 years ago, which is that if you get just get a bubble vibrating at the right frequency, then it will start luminescing. And there were all these theories about how does this work. And these guys have been doing it for millions of years, right? So it's exactly the same phenomenon. So again, whenever you come up with a clever idea, nature's probably got there first. And this is another example.
But what's the temperature of this bubble?
I don't know. So they say the temperature of the sun. I don't know exactly. They might just be making it up. But it is true. So, but this collapse of bubbles near boundaries is very interesting because they actually spike and they give rise to. This is why submarines, when depth charges do in submarines, it's not from the actual explosion, it's from the collapse of bubbles near the hull. It turns out you get really high pressures as bubbles collapse near boundaries, and that's what does the damage. But we'll come to that problem later. So that was using bubbles to hunt. So these guys clearly care about surface tension. And here's another thing that cares about surface tension. So these guys use drops.
Weapons to dispatch prey. Others employ the finesse of a marksman. The archer fish uses a water pistol. It makes a gun barrel by pressing its tongue against a groove in its mouth. It closes its gills to force out the water. It's accurate up to 2 meters.
2 meters?
Yep, there's a great shot at the end. But again, you have to get this right? And if the thing breaks off in a different way, you're going to get the trajectory is going to be off. So they really have to get it right. And again, they've simply evolved to do this. I don't think they're doing their math before.
For the way light bends at the boundary between water and air, which appears to shift the position of its target. By some amazing computation, it changes its firing angle to compensate for this optical illusion.
It's like sophisticated filming, so they
Yeah.
several cameras.
This is great.
Archers target anything that moves or glows.
It's also an alpha fiction.
That's right. So, right. So those are some. Again, I'm always amazed by the sort of the range of mechanisms which nature uses, and those are some nice examples. But we discussed yesterday. So these creatures that will breathe underwater. But they're so water repellent, they trap a layer of air through which they breathe. So they basically have an external lung which is supported by water repellency. And then they're diving spiders. So these guys basically form a net, and then which captures a bubble, and they use this as sort of diving chamber. And so they hunt underwater, and they return to this bubble to breathe, so that they don't have to surface on each dive. Okay, and we've discussed a little natural strategies for water repellency, and we'll get into that. The hydraulics of trees is strongly influenced by surface tension. So whenever you have very small constriction, so when you have a pathway of fluid which is very small relative to the capillary length, which we'll define soon, basically anything on the order of millimeters or smaller, then surface tension is going to come into play if there are interfaces. Okay? And so lungs and surfactants, so when in infants, it turns out a common difficulty they have is taking their first breath. It's because they have to create the energy required to coat the lungs. So basically, because you're going from something with no surface energy to basically breathing air into the lungs, you're creating a huge surface area, and oftentimes they aren't strong enough to do this, particularly premature children, and so they actually inject surfactants. So surfactants is something which decreases the surface tension, so it decreases this energetic cost of expanding the lungs. Okay, so who else cares about surface tension? So it actually comes up in geophysics and environmental science. I wrote a review on this recently. So the dynamics of raindrops, we all know that rain is important. I was curious to learn that there's even some suggestion that there's feedback between the rain and life itself. So turns out that most biomaterial, so again, any spores or anything created by living creatures is surface active, so it tends to stick to the surface of drops and bubbles. And so as a result, whenever you have a lot of interfaces, so for example in the surf zone where you have breaking waves, there's a lot of biomaterial accumulated, and a lot of the exchange between the biosphere on the terrestrial and the aquatic biosphere happens in the surf zone. Okay? And there's even suggestion that rain will not form. Let's say rain forms much more easily if there's dust in the atmosphere, there's stuff floating around, and biomaterial in particular. And so when you have a forest, it will kick up lots of dust and and so increase the likelihood of rain. So in some sense, there's actually a feedback between rain and life itself. Okay, in terms of modeling early life, there's suggestion that so we know that you can have the spontaneous generation of amino acids if you take carbon dioxide from as I say, spontaneous creation of amino acids from inorganic materials, so from carbon, from nitrogen, from oxygen, such as one expects to have in the early Earth, just by sparking it. So they've done this experiment. You just take these things, put it in a spark chamber, and you get the spontaneous creation of amino acids, which is a basic building block of life, but then they have to combine. And so as you get these lower order life forms being created, the likelihood of them combining and making larger ones is going to be higher if they're at an interface. Okay? And also if they're contained. And so there's suggestion that the first vesicles, which would contain such material, come from bubbles passing through interfaces. They come through interfaces. If these interfaces have surfactant on them, have this chemical, then if the bubble goes up and then falls through, then you'll get a bilayer of surfactant, and this could be the first model of the vesicle. Okay? And so there is some suggestion that interfacial effects are important in models of early life. Okay? Okay, so all of these things, oil recovery, so there you're pushing oil through, or water through oily sand or oily ground, and the ground has very small pore space. It's basically flow through porous media. When you have interfacial flow through porous media, the interfacial effects are dominant, so this is true for both oil recovery, carbon sequestration, and groundwater flows. The early work on water repellency was done by people who are designing insecticides, and it's kind of a tricky problem because you want to kill the insects but not harm the plants, and you're basically hitting them with a toxic chemical, and typically plants and animals co-evolve. So basically the insects will evolve so that their surface is almost identical to that of its host. Okay? And so they're equally water repellent. And so you have to try and find chemicals which will stick to one and leave the other one unharmed. Right? Okay, so water repellency of soils. There's if you have chemical leaching, so if you have some soil which is rich in nutrients, and then if you get droughts, and then you have some rain, then it can be that you'll get leaching of all of the valuable chemicals, and so you'll get the spreading of deserts as a result of interfacial effects. You then basically get a water repellent, so the soil starts to become water repellent, and the water just rolls off and collects all of the nutrients which you actually want to stick there. So it comes in there. Oil spills. So this is a good one. The oil spill in the Gulf. So normally what was unusual about the latest BP spill was that it was very deep, right? And normally you have an oil spill in a shallow region and it looks like this. So you have some source of fluid and it basically just goes up and spreads at the surface. So there you know at least that the oil is going to be confined to the surface. The difference in the BP spill was that it was at great depth, and the problem is they injected dispersants. So if it was at great depth, it would be fine if it had been coherent, if you just had a plume like this, because it would have just gone to the surface. But they noticed that the flux here was very large compared to the flux here. Okay? And it was in fact a factor of 10, and they couldn't figure out why. The reason why is they put in chemicals which caused the oil to break up into tiny drops. So instead of having this stream, you have this cloud of drops going up, and these drops, when they move through a stratified ambient, they actually go throughout the water column. So they're basically entraining. They're of course buoyant relative to the ambient, but they entrain. This basically goes up as a turbulent jet, and so entrains fluid as it goes, and then you get these neutral heights, these regions where the density, the net density of the cloud matches that of the ambient, so it intrudes. And so you get these discrete intrusion layers, and so this oil, instead of surfacing as it would here or here, goes throughout the water column. So then these dispersants are simply surfactants. So again, they basically decrease the surface tension, so they make it easier for the stuff to break up. So this was the big problem in this. And so when this happened, I lectured on this in my class, and then I found out that my old friend Andy Woods, who's director of BP research now, knew that as well, and so they gave him something like $1 million for figuring out why it was happening. It's actually pretty straightforward if you know anything about surface tension. Okay, so BP also, they came, wait, I'm being filmed. I'll just stop. Stop now. Okay. Something that I'm actually working on now is disease transmission via droplet exhalation. So I have a postdoc who's done some rather disturbing experiments where they look at sneezing and coughing events, and turns out this is the range of the pathogen-bearing droplets is strongly determined by the interfacial dynamics, because they're basically trapped on these drops which are carried in a cloud. Okay, so dynamics of magma chambers and volcanoes. So this is another geophysical setting where surface tension comes in. Basically, if you have a volcano, it's degassing. That is to say, the pressure is decreasing as it rises, and so gas is coming out of solution. So then you have these sort of bubbly column of fluid coming up from a volcano. Okay, so you have this two-phase flow, and this can give rise to, if the bubbles grow enough, then you can get a substantial volume fraction, and it'll actually fill the entire column, and then you'll get these eruptions happening in a regular way, and it's basically a divide between fluid as the fluid and the gas are expelled. And my favorite, this is my favorite, have you ever heard of these ones? The exploding lakes of Cameroon? Okay, so this is a nice mystery. So here's a mountain, And there's a lake at the surface. And this mountain is an extinct volcano. Okay? And so there are a couple of villages along the sides. And they wake up one morning and everyone in the village is dead. Okay? So that's the mystery. How did that happen? It's like hundreds of people, and it happened several times before they figured out what was going on. Okay, and this is actually, so this is the explanation. So again, it's an extinct volcano, so we imagine there's some sort of source of magma, and then you have carbon dioxide leaching into the lake, okay, from beneath. So if we do a zoom on the lake, so this is the lake now, and we have this carbon dioxide going in. So you actually get a layer at the bottom which is very rich in carbon dioxide. And the so this is then like basically like a Coke bottle. You have this carbon dioxide. It's rich in carbon dioxide, but under pressure. But if you can perturb it some way, and basically they think there was some wind causing the sloshing mode, and then so then you basically perturb this interface, and so you decrease the pressure locally, which means you get this, so the bubbles start. Okay, and so then there's this eruption of bubbles, and the only clue they had was that in the morning they looked and they saw that the lake looked like it had belched, like literally the water level had gone up by a meter and then come down. And this corresponded to the degassing. So then you basically get this bubbly plume, and the entire, all of this carbon dioxide was released at once. Okay? So you get this cloud of carbon dioxide coming up. Carbon dioxide is heavy relative to air, so it then poured down the mountain and suffocated the people in the villages. So there's a, and that was I think in the 90s. And so what they do now, or in the 80s, and what they do now is and this will only happen in sort of equatorial regions where you're constantly heating from above. So they're basically getting more and more stratified, so there's no overturning of the lakes. So what they do now is they artificially bubble the lake. So they basically have bubbles going all year, and so this basically mixes the lake and keeps this sort of stratification from happening. Okay. Okay. So, so if we look more recently at who's interested in surface tension, most of the funding going into surface tension research was coming in through the space agencies. So in outer space, of course, so I've said that surface tension dominates gravity when we're small relative to a raindrop, but there is no gravity in outer space, so surface tension is actually very important. And so if you have if there's for example, a fluid spill on a space shuttle, the fluid will just drift around. It won't fall to the floor. It'll just drift around. It can do all sorts of damage to the electronics. And so you can actually get the fluid to move using capillary effects. So if you have a drop here in zero gravity, and it turns out if you put a heat source here, it will spontaneously move towards the heat source. And we'll work through that problem. But so here, just to show to you that, oh wait, we missed this one. Let's take a look at the wine tears. Yeah, so these are the tiers, in case my explanation wasn't clear. It's not very good looking wine though. So these are again from Multimedia fluid dynamics. But so now he's just generated a thin film, and now we're going to zoom in and see what you see on the film. So you can do this yourself over dinner. And you see these tears forming along the side of the glass. And that's owing to the depletion of alcohol, and so the increase of surface tension in the thin film. Okay, and so here's a large, so this is an air balloon in zero gravity. So you basically, you basically pop. Yeah, water balloon, yeah, and you just pop the elastic band, but the fluid just floats around because it wants to stay together because of surface tension, yeah. Okay, and so we mentioned when we were looking at the pistol shrimp, these bubbles exploding near solid surfaces can do a lot of damage. If you look at propellers on boats, there's often pock marks on them. This is because of the explosion of cavitation bubbles, or the implosion of cavitation bubbles near the propellers. Okay, and we mentioned the damage done by submarines by depth charges is similar. It's from the collapse of bubbles. Okay. So now, there's been a huge resurgence and interest in wetting effects, and a lot of it's being done by David QUÉRÉ and people in Paris. They're basically designing superhydrophobic surfaces. They can do this now because of advances in microfabrication techniques, but they are basic, so they can now design self-cleaning windows, drag-reducing surfaces, erosion-resistant surfaces, by combining chemistry and texture. And their ideas are coming from nature. They're looking to see how leaves do it, how bugs do it. Okay, and then we have lab-on-a-chip technology, so you have medical diagnostics and drug delivery, so patches you can put on your arm which actually deliver drugs automatically. And again, here you're trying to move fluids around on a small scale using capillary forces, something which nature has been doing for a long time. Okay, and we have so microfluidics, continuous and discrete fluid transport and mixing. So again, moving fluids around on a small scale. Oh wait, so here, for example, oops. What just happened there? Did I just accidentally move a slide? I did just move a slide somehow. There we go. Yeah, so here, if we look at, these are drops bouncing on a fluid surface. You can imagine sorting. So let's imagine you want to get drops of all one size, and you want to turn them into medicine of a given volume. So actually by putting fluid drops on a surface and vibrating in the right frequency, you're going to select, because only some of them will bounce. And there you can see merger giving rise to, and then giving rise to sorting. Okay? And you can also mix with a process like this. So this would be called discrete microfluidics, because you're looking at the microfluidics of individual parcels of fluid or droplets. So here you start with the oil water, and you can basically emulsify it via bouncing. Okay, and so another area which is well funded in terms of for surface tension research is they're interested in tracking submarines. So as we mentioned with Pliny the Elder, you have, whenever you sweep up a biomaterial to the surface, you make the surface effectively elastic, and this suppresses small capillary waves. Okay, inkjet printing, we all know about that. Again, strongly involves capillary effect. So you basically want a stream of drops of uniform size. So the Rayleigh plateau instability dominates the dynamics there. And then we have the bubble computer. So this is something that was developed by a graduate student of mine. I don't actually know anything about computers, but if you do, then maybe you'll be able to tell me how this would function as a computer. But it's kind of a cool video. So here, the bits are the bubbles, okay? So this is, they're able to transfer information via the, and I think the Russians did a lot of work on this. In the 60s, they were interested in having computers that would function even in the case of electrical blackout. Okay, 5-minute break. Coffee break.